Hi everyone, my name is Tingyu. I'm going to present our work, Weakly Supervised Face Naming with Symmetry-Enhanced Contrastive Loss by Tingyu, Tinne, Tuytelaars, and Moens from KU Leuven. First, about the task. We studied the weakly supervised face name alignment task. We were given an image with faces and caption with names. Our goal would be to align faces to names without knowing the ground truth annotation during training. Our first model, Symmetry-Enhanced Contrastive Learning-Based Alignment Model, SECLA, is here. For input, we were given image I and caption S, with face set F and name set N. We use pre-trained FaceNet and BERT as feature extractors and MLP as projectors. We compute the dense similarity of face set F and name set N as the sum over max of projected features. To train our model, we first use a contrastive loss bidirectionally to maximize the dense similarity between face set F and name set N. Because the dense similarity measure actually requires a computation of max operator, so we do it bidirectionally to strengthen the symmetry. We also use agreement loss to further strengthen the symmetry as MSE over the diagonal elements of the D matrix, which results from computation of dense similarity. Our second model, SECLA-B, uses two-stage training with bootstrapping. At stage 1, we train a SECLA on an easy subset, like one name and one face. Then we keep the unique names and corresponding faces from stage 1 training. At stage 2, for names we've seen before, we match faces using stage 1 model in each batch. After matching, given matched names, matched faces, and retrieved prototype faces, we do a similar contrastive loss to push the prototype faces that do not correspond to the current matched faces away from the matched names. We do it bidirectionally. Similarly, if the prototype do not correspond to the current face, we push them away. Then for matched faces, we use those two losses. And for unmatched faces, we use the same loss from stage 1 training. Then first, the main results. It can be seen that our model achieves the SOTA performance on both datasets. And when we remove the agreement loss from SECLA, the performance drops. We indeed need to strengthen the symmetry in this way. And our SECLA-B improves the performance of SECLA further. On LFW dataset with at least two faces, the previous SOTA achieves 47% F1, SECLA achieves 67% F1. There were just too many unique names in this subset, so future study required. As for SECLA-B, it can be seen that only when all the ingredients are included, we can achieve the best performance. Let's see some examples. First, a failure case. We were given an image with two faces and a caption with three names. We were not given the ground truth label. The correct alignment would just be naming red to red box, naming blue to blue box, and naming yellow to no face. However, our model aligns naming red correctly, the other two wrongly. The reason is that naming yellow appears twice without face in the image, naming blue appears 8 times, 4 out of 8 without face in image in the dataset. These are just two very unusual names. Our model also did very well in some cases, like this one. We were given 6 faces with 3 names to align, and there were no ground truth labels or captions during training in this dataset. Let's zoom in a bit. And our model correctly aligned all the names to all the faces in this very difficult task. For conclusion, our model achieved the SOTA performance, and we found symmetry is very important for this weakly supervised alignment task. And we also found that learning like humans do, from easy to difficult with bootstrapping, help us to learn better alignments. For future works, we can adapt our model to other multimodal news understanding tasks, like multimodal summarization, news image captioning. And we can explore the two-stage learning framework for other tasks. Thank you for listening.